Having learned several techniques for solving first-order equations, we now want to turn our attention to solving higher-order equations. Now we'll start our investigation of higher order by looking at second-order linear differential equations. As you can see, we've got a second derivative, first derivative, and the function itself. That's kind of where it gets its name linear. Notice all their coefficients are some functions of x. There's not any y's in any of that. And it's equal to some function of x. So, here is an example of one, and this is what we're talking about. Second derivative, first derivative, function, all their coefficients are functions of x. Here's another one. Can you recognize the coefficient of y double prime is 1? That's technically a function of x. Coefficient of y prime is a 4. Coefficient of y is a 4. Those technically are functions of x. Look at this last one. You notice anything particular about that? Here's the second derivative, whose coefficient is 1. Here's the derivative, whose coefficient is not a function of x. It is not a second order linear differential equation. Now we'll be using the standard form quite a bit, and this is what we mean by the standard form. On the second derivative, the coefficient is a 1. And it goes in order: second derivative, first derivative, function itself, and then equals some function of x. So, take a look at this. How do we put these into standard form? On the one on the left, to put this in standard form, this whole term needs to come over to the other side. So if we subtract that, and we do not want a coefficient of x on the second derivative, so we will divide through by that, and we have standard form. Here's our second derivative with a coefficient of 1. Here's the first derivative, whose coefficient is negative 2x. Let me point out that's the px in the standard form equation. And of course the qx would be a 0 in this case. On the second one, we need to move everything to the left, divide through by x, and we have our standard form. Well, divide through by x now. In standard form, the coefficient of y double prime, 1. The coefficient of y prime needs to be some function of x. There's no y, so that would be a 0. And then the constant is some function of x. Now the first technique that we're going to learn is really the big brother of what we learned back in Calculus 1, and that is substitution. So we're going to do the substitution technique. Now it just so happens, and we'll talk about this in class, when our second order equation does not explicitly contain a y. So you see here we've got a second derivative, we have a first derivative, but there is no y. There's some x's, but there's no y. We're just going to blindly, for right now, do the substitution. Let y prime equal v. Now, y is a function of x, v is a function of x. So we basically are saying y prime of x equals v of x. I'll write that down for you. Y prime with respect to x equals v with respect to x. Same thing here. The second derivative of y with respect to x would be the first derivative of v with respect to x. Notice we get that just by differentiating y prime equals v. And so that's our first technique. And let's see how that works. So we're going to just recognize that this needs the substitution y prime equals v, which means y double prime would be v prime. So we're going to substitute in place of this y double prime a v prime, and in place of this y prime a v. So that substitution produces this. Notice that now this is a first order linear equation. So we solve that like we learned in an earlier chapter. Find the integrating factor. Rewrite the left-hand side as the integrating factor times the function, in this case v. Rewrite the right-hand side as what was there, f of x, times the integrating factor, and do the integral of that. Now we want to solve for v, and then unsubstitute, just like we did back in Calculus 1, and replace do the integral of that to solve for the y prime. And that's basically our technique. Here's another one to try out. We'll begin by using the substitution y prime equals v. So y double prime is v prime. Do the substitution. Now you recognize that in this one we've got v squared minus v. Now remember, we're looking for v as a function of x. So this is the two functions v and x now. And v squared minus v tells us we have some constant solutions wherever that's equal to 0, which would be v equals 0 and v equals 1. We'll keep that in mind for later. However, it is separable. So if we divide both sides by v squared minus v, multiply both sides by dx, we end up with a separable equation. We can integrate both sides, solve for the v, and then resubstitute. Once we get y prime, we integrate and finish solving. We could do some rewriting on this. Again, it's kind of okay like it is. However, we'll use A to be the negative C2 and B to be C3, and we'll come up with a little nicer looking equation. Incorporating our constant solutions that we mentioned earlier, when v equals 0, that means y prime is 0. So we'd end up with just y equals some constant. Now, that is not tied up in the function that we came up with, so we would want to list that as a separate entity. However, this one, y equals x plus c, is also a new one. So our answer would be y equals 1 over a ln 1 plus ax plus b, or y equals c, or y equals x plus c. I'm not going to pull up the graph, but this is just something that you can do on your own. Now notice, on this initial value problem, we have two conditions. We know the function value and we know a derivative value. And this is true with all second order equations. We have to be given two initial conditions, both a function value and a known derivative value, in order to solve an initial value problem. So anyway, we still do the same substitution. I'm going to go through this a little quicker without all the details described because we've already done a couple of them. We do the substitution. We solve that. This is a first order linear, so we find the integrating factor, rewrite the equation, solve for v. We take the initial conditions that we're given here, y prime 0 equals 2, and substitute those to find the first constant. We go ahead and rewrite our function y prime using that constant. Then we finish integrating. And we find the second constant the same way, using the other initial value and solving for C2. And so there is our specific function that we were trying to recover.